Hello everybody. Again, my name is Martin Kocour, and today I'm going to present our automatic processing pipeline for collecting and annotating air traffic voice communication data. This work is part of ATCO project, as Javier already mentioned, and I will start. Oh, wait a bit. How I go? Okay, so I will directly start by describing the pipeline. So in ATCO project, we collaborate with the community of radio amateurs who volunteer to capture the voice communication data directly from the air, and these data are then processed by our pipeline, which is a cascade of standalone components. At the beginning of the pre-processing, we have some pre-processing steps which consist of segmentation, demodulation, and volume control block. Then the audio signal is filtered based on signal to noise ratio level. The segmented speech is then further processed by our diarization component or system, where we basically split the speakers where we basically split the audio based on the speaker terms. The audio signal or the segmented audio signal is then further processed by our automatic speech recognition, where we basically converts the audio signal into text transcripts. The text transcripts is then further processed by our NLP modules, and also we discard non-English utterances from in our pipeline. Yeah, the collected data are then shared with the community of researchers and our industry partners in ATCO project. Yeah, maybe I can move on. So why do we need the automatic processing pipeline? We need it because purely manual annotation of large amount of ATC data is slow and costly, since the speech is noisy and contains a lot of accented English. The air traffic communication is also quite specific. It contains specific phrases and vocabulary, and that is why the annotator needs to have some basic knowledge about air traffic communication. In this work, we proposed the solution where we use machine learning concepts to basically accelerate the process of annotation. And we also incorporate the supervised data to basically improve the performance of our systems. Okay, so now let me describe the automatic speech recognition for air traffic communication. In this work, we use hybrid speech recognizer, where temporal dynamics of speech are modeled by hidden mark models. The recognizer consists of acoustic model and a recognition network. The output of the recognition network is also known as HCLG graph. We will see it later in this presentation. The output of the recognizer is a lattice, which is a compact structure containing all possible hypotheses. Okay, automatic speech recognition is the most essential component in our pipeline because other components quite heavily depends on it. This is the reason why we focus on improving the performance by providing some contextual information from ADSB messages of airplanes. It works like it's depicted in this figure. So first, we have a recording. We have a recording where we know its GPS coordinates and the timestamp. With this information, we query the OpenSky network database, which provides us a list of call signs. These call signs are then verbalized and used for enhancing the ASR module. So why we choose? So we choose the call signs because we believe that the call sign is the most essential part of the communication. This and in this and also it is quite challenging for our ASR to recognize it correctly because there exist more than 7,000 airline designators, which also sounds similar, like arrowhead, arrowjet, arrow, red arrows. These words sound similar for our to our recognizer. There is also another issue that ATC controllers also use unofficial variants of airline designators, like Lufthansa is sometimes pronounced as Hansa, or Speedbird is sometimes pronounced as a bird. And also shortening of call sign is quite frequent. All of these issues make the call sign recognition difficult. So that's why we focus on it. And yeah. So on the other hand, if we know the correct call sign, we can use it to build some more specific applications, such as tracking of specific airplane in the communication of pilots and ATCOs. We can also build a search engine for incident investigations. We can easily detect some communication errors, or we can use the call sign recognizer just in the cockpit to notify the pilot that the message was addressed directly to him. Yeah, so how the call sign boosting works. In this work, we use an approach which is called Lattice boosting, where the call sign is first verbalized into a word sequence. Each word sequence is then boosted as a whole snippet of text. Each boosted sequence is represented as a specific path with score discounts. And the boosting is based on WFST composition of the original lattice and the boosting graph. An example of a boosting graph is depicted in this figure. Here we have just one call sign, CSA 3 alpha Bravo, which is verbalized into two different forms, CSA alpha Bravo and CSA 3 alpha Bravo. We can also see the score discounts -6, -4, -4, which basically ensures that this path becomes more probable in the lattice after we do the WFST composition. Yeah, this approach has one drawback, and it is that the word sequence must be present in the original lattice in order to be boosted. However, this bottleneck or this drawback might be overcome by HCLG boosting, so by boosting of the recognition network. Here we basically increase the chance that the boosted sequence will appear in the original lattice just again by doing the WFST composition of another boosting graph with the recognition network. The difference is that this boosting graph in this boosting is different. It is more simple. It contains only words from vocabulary, and we boost here only some specific words like call sign designators. So we don't boost whole sequence, but just the single words. And the graph needs to be small because the WFST composition of recognition network and the boosting graph is a heavy operation. If we want to do it like per each utterance, we need to do it quickly. So that's the reason why the graph is much simpler than in lattice boosting. Okay, so we measured the effect of call sign boosting on live ATC test set and public ATCO2 test set in terms of word error rate and call sign accuracy. The effect of call sign boosting is best depicted when we compare the call sign accuracy without any boosting and when we compare it with the cascade of HCLG and lattice boosting, either on live ATC test set or on ATCO2 test set. On live ATC test set, we are able to decrease the call sign accuracy by almost 30% by just doing the HCLG and lattice boosting. And on ATCO2 test set, we were able to increase the accuracy by almost 12%. Yeah, since we have more than 12 hundreds of hours of untranscribed speech, we can further improve our ASR by semi-supervised training. Here, the idea is that we can leverage the word level confidences to scale the gradient in break propagation training. In this table, we have results for semi-supervised training. So first, we have a seed system, which basically transcribes our untranscribed speech data. Then we apply the semi-supervised learning, which already increased the performance of our system by more than by almost 3% on ATCO 2 test set. Sorry, the pointer is some lags. Then we also can further improve the performance of ASR by cascade of HCLG and Lattice boosting. I'm sorry for the pointer, but it's still laggy. Okay. Then we have another component in our pipeline, which is an English language detector. Here, the goal is to have the minimum number of non-English utterances in collected database. In this work, we tried two different approaches. First, we tried the state-of-the-art approach, which is purely acoustic ALD system with neural network embeddings called X-vectors. We also tried our own approach, which is based on document embeddings, which are extracted directly from ASR output. Here, the idea is that the word level statistics are accumulated based on confusion networks, which comes from ASR output. And we apply TF-IDF rescoring to basically deviate or scale down the most frequent words. The decision is made based on logistic regression. The performance of our ALD system is depicted here in this on this depth curve. The blue one is the state-of-the-art approach with X-vectors, while the orange one is our approach where we use document embeddings. On the x-axis, we have a probability of false alarm, and on the y-axis, we have a probability of miss. Since we are interested to, or our goal is to discard all non-English utterances, while we can allow some misses. This is the reason why we tune our system in such a way that we have low false alarms, but we can allow quite higher misses. And you can also see on this figure that the state-of-the-art approach is worse than our approach with document embeddings. Okay, finally, I would like to describe our NLP methods. Here, we are trying to extract knowledge directly from the ASR output, and we are focusing on 3 different tasks. I already mentioned the call sign recognition, but we are also focusing on ATCO pilot classification, and we also would like to introduce the ATC-entity recognition. So our call sign recognition is based on BERT-like models. The input for the model is basically ASR transcript and the surveillance data. We use 2-pass call sign extraction, where in the first phase we take the call sign in the ASR transcripts by the name entity recognition. Here, with the BERT model, and then we just map the call sign into ECAL code like Hansa 8-1 Juliet. Yeah. However, the ASR output might contain some errors. So that is the reason why we also include the surveillance data, which basically can provide us some more contextual information, and we can utilize it to just improve the call sign recognition. I already showed you the performance of the call sign recognition, so I would like to move to another NLP method, which is ATCO pilot classification. Here we are trying to utilize that the pilots use slightly different vocabulary than ATCOs. Again, we train our models on top of ASR output. In this work, we compare 3 different approaches. First is a TF-IDF model with binary logistic regression. Then we use convolutional neural networks. And we also tried pre-trained and fine-tuned BERT model. You can see that the BERT model performs the best in terms of classification accuracy. On ATCO2 testset, we are able to recognize ATCOs and pilot with the accuracy of 91%. And on live ATC testset, we are able to recognize ATCOs and pilots with the accuracy of 87%. Yeah, more information may be found in my colleague work, which was submitted to ICASP this year. Right now, we are basically working yet on yet another NLP method. So I already mentioned that we are interested in cosines, but we would like to also recognize other ATC entities like commands and its values. Right now, we are using a BERT model, which is trained on very little amount of data because we are missing the data. And we are currently trying to basically build a bigger database to be able to train more reliable system. Here I have just a table with some preliminary experiment. Here we use F1 scores, and we are trying to recognize a cosine command and value. And you can see that on ATCO2 testset, we have quite good performance. Yeah, by this, I would like to I think that we have another issue. Yeah, okay, thank you. So by this, I would like to summarize what we have done so far. So we have created an operating pipeline for processing and automatically annotating the ATCO and pilot air traffic control audio data. The pipeline is able to discard noisy and non-English speech. It generates automatic transcripts. It extracts call sign code in equal format directly from the communication or from the speech signal. And it is also able to classify the speakers, either ATCO or pilot. So far, we have collected more than 2,000 hours in ATCO2 project. And in the future, we would like to focus more on extracting higher level ATC-related entities, such as commands and values. And let me conclude my presentation by my personal wish that perhaps one day the voice tools will finally serve pilots and ATCOs. Yeah, and yeah, that's all. Thank you for your attention. And now it's time for your questions.